Good afternoon, everyone. I'm Meenakshi, and it is a pleasure to welcome you all on behalf of eMobility Plus and First View Group to today's insightful webinar on modeling hydrogen fuel cells and electrolyzers. First and foremost, we would like to extend our sincere gratitude to our partner, COMSOL, for their continued support in making this session possible. Before we dive into the session, I am pleased to introduce our esteemed speaker today, Dr. Rustam Shekhar, Application Manager at COMSOL Multiphysics Private Limited. Dr. Rustam is the Applications Manager at COMSOL, specializing in electrochemistry and battery simulation. His expertise includes electrode microstructure and cell and packing level modeling. Now, a brief overview of today's session. The global push for cleaner energy is accelerating the development of hydrogen technologies and the infrastructure to support them. Because direct measurement is often challenging in hydrogen and fuel cell R&D, modeling and simulation provide powerful alternatives. In this session, Dr. Shekhar will demonstrate how to use COMSOL Multiphysics to model and optimize electrolyzer and fuel cells designed for improved performance under different operating conditions. Through real-world samples, you learn step by step how to build models, analyze results, and visualize performance. This session will also feature a demo where you'll see how to set up and solve a model in this software. Following the presentation, we'll host a Q&A session where Dr. Rustam will respond to your questions submitted in the Q&A box. So feel free to drop in your questions and queries anytime during this session. Now, it is my pleasure to hand over the session to our speaker, Dr. Rustam. The floor is all yours.
Yep, thanks, Meenakshi, for introduction and opening up the session for today's webinar. So today, as Meenakshi mentioned, we will be talking about the modeling fuel cells and electrolyzer, and we'll see how that can be approached in COMSOL, that is a multi-physics platform. So we will see what sort of fuel cells we can model, how we'll approach them, and then we'll see one case study, which is from one of the automotive manufacturer. So you'll see how they utilize COMSOL for their fuel cells applications. So to start with and to give you a context why we are discussing fuel cells and electrolyzers. So right now we are working on the IC engines which are running on the hydrocarbons. But as in promise to go for the net zero emissions, we want to go towards some solutions which will give you zero emissions, and then towards this side, we generally see we can go towards the electrification of those vehicles or for the HTC applications. So in the journey of electrifications, then right now we see there's a phase of batteries where batteries are being used to electrify the vehicle. And in this electrification features where we are using lithium-ion batteries, they are placed in the vehicle, and then we have to charge the battery and run the vehicle. But after what we see, there may be some range anxiety, there may be some performance issues. So in the journey of electrification, batteries are the first step. And next step, which you can see, may be governed by the fuel cells. So fuel cells are very much similar to what we have like a conversion device. So it's electrochemical conversion device. So in electrochemically, we are trying to convert fuel energy or fuel into electrical energy. And when we want to obtain that fuel, then fuel cell device. So that same device, if we operate in a different manner, or we change the design a little bit, then we can produce that hydrogen also. So then the fuel cells and electrolyzers are a device where we can generate hydrogen by renewable sources, and then we can use them into the fuel cells to power our vehicle, power our stationary applications, or power our entire let's say platforms. So here, what we can see, there may be one production part where I want to produce hydrogen. So hydrogen can be produced by different sources, and as you change the source, based on the source, we call that particular hydrogen with a, let's say, blue hydrogen. We can call it, let's say, gray hydrogen, green hydrogen. So that way, type of hydrogen changes when we change the type of production. So here we can discuss about the type of production of hydrogen, which is green hydrogen, where we are producing hydrogen with the water splitting, or we are producing from the water. So we just provide energy. That energy can come from solar, wind, thermal, or any other sources. So what we say, we have a renewable source like solar that is giving you energy. Energy is converting hydrogen. Now that hydrogen can be stored, can be transported towards wherever we are using. So if you see stationary applications, then they can be provided to the grids. If we are using for the mobile application, then we can store them into a container like hydrogen tanks. Again, tanks can be that tank can be there in a different format like liquid, gas, and solids. So if you see around hydrogen, there are three major things like production, storage, and transportation, and ultimately we want to consume it. So we can talk about this complete ecosystem where we see production and consumption and storage and transportation. So here we will focus on production of green hydrogen, which can be done by the electrolyzers, and then we want to use it in the fuel cells. So we'll see how modeling can help you to predict the performance and the life of those particular devices. So to start with, I just want to know from the audience that, okay, right now are they, so there will be a poll question launched by our team. So we just want to know that are you regular user of simulation tool, or you're evaluating on simulation tool, you're new to simulations. So that will help us to understand that, okay, at what depth we have to go to explain one particular phenomenon or scenario. So if you will be new to simulations, then we can talk about how what simulation does. And if you already know simulations, then we can talk about like applications most of the part. So please, can we launch this first poll question? So I will know the responses. So while you are responding to this poll, I can set up the context of it. So let's say if you are from the, let's say A, so where you are a regular user of the simulation tools. So here you may be facing some problem. So then you can let us know. So you can let us know your problems that you are facing in the questions tab. If COMSOL can help you to resolve those problems, we can discuss that. If you're new to simulations, then we can talk about how simulation can help you, and then you can evaluate any simulation tool. In this case, COMSOL you can evaluate. And sometimes you may attend the sessions just for your personal interest. So then that can be a one that also can be a one good cause to attend these kind of sessions where we can be interactive. So you can let us know what real problem people are thinking, and then we can also provide the solutions, and we can have this session interactively. If you're evaluating a simulation tool for your any ongoing and upcoming projects, so that also may be interesting for us, where you'll see how we can help you to evaluate or to get your desired goal. So please register your responses to this poll question. So once we'll get the responses, we can go ahead with our presentation. We request you to respond to this poll. I hope we got sufficient responses. So can we close the poll?
Sure. We'll close the poll now. We are still getting responses, Dr. Rustam.
Yeah, sure. Okay.
The poll will stay live and people can keep responding to the poll and we can proceed.
Yeah, sure. Thank you. So now we'll see when it comes to the fuel cells and electrolyzer systems. So what people are thinking of, so you can see the major technology which people are focusing or working on. It's based on the membrane which they're using. So if the membrane is conducting a proton to have this kind of energy conversion, so then it's a proton exchange membrane. When we see the ions which is conducting is hydroxide or OH negative ions, then we can say hydroxide exchange or alkaline fuel cells. When ions is in oxide form, then we have these peroxide fuel cells, and we have molten carbonate fuel cells also. In some cases, you will see phosphoric acid and then other corresponding water electrolyzer or fuel cell system. So we can see majorly there are 4 or 5 technology, but as in this particular area is under research. So you may find some other technologies also which are dominant in this area or which may become dominant in this area. One more classification which we can see based on the operating temperature. So if you see there are 2 technology called SOFCs and MCFCs, both are operating at higher temperature, and wherein the other technologies are operating at lower temperature. So the technology which is operating at higher temperature having their own pros and cons, and technology which is operating at low temperature also may have their own pros and cons. So that way, when one device comes with their own properties and the problems, then we have to tackle those problems to make that particular device more efficient. So here, if you talk about SOFC, they are very high temperature fuel cells and they are high in efficiency. But if you will think of you want to use them for your mobile application, so then no one wants to carry a hot ball which is around 800 degrees Celsius, and then it is dangerous as well. So people move towards PEM fuel cell, which are operating around 80 degrees Celsius, or sometimes high temperature fuel cells or operate around 160 degrees Celsius. But when we go below 100 degrees Celsius, then always we will deal with a two-phase flow problem where water flooding will be there, and then you may lose your efficiency. Sometimes the device may become dysfunctional also. So this way, you can figure out the technology which you are working on, and if you are working on a different technology which is not listed here or which is very new or we can say niche for, and then you still want to work on, then you can let us know that particular technology name into the questions tab. So you can have one questions tab where you can ask question. So where you can let us know about this also if you're working on any different type of fuel cells also. So generally, we say fuel cells and electrolyzer are the same device, only the mode of operation or the current. If we drop the current, then it is in the fuel cell mode. If we, let's say, provide current, then it's in electrolyzer mode. And based on that, it depends on let's say, potential conditions or the thermodynamic conditions, and some flow arrangements may be changed in this case. So to know what people are working on and then at what application people may work on. So we can focus on one particular type of fuel cells. For that, I may need one more help from your side, which will be answering to this poll, where I just want to know that you want to work on a fuel cell or electrolyzer for a mobile application, which is stationary, which is vehicle or a two-wheeler, three-wheeler, four-wheeler, or like a larger vehicle like ships, planes. You may work on the fuel cells or electrolyzer for the stationary applications like power grids or any other specific application that you can let us know by chat. So I request my team to launch this poll. So then we'll know responses that, okay, with respect to which application area we have to talk about today. So then we can have the more examples towards that particular area, and I can let you know the industry wise what people are working on. So then we can focus our discussion on that particular part. So please
So
launch.
we're launching our poll number 2.
Yeah. Okay, so I think I can see some responses also where people say they work on automotive application. Some people say they want to see about all 3 applications, but majority of them are working on automotive sites. Few of them are grid sites. So yeah, so I can, if I want to quantify like what is the majority wise, it is automotive and the stationary one. So yeah, I think one question is that poll is launched. Yep, we can see the poll. Fine. So I think let's just start with a discussion where we'll focus on the automotive applications. And then if you have any specific question, let us know. So I can see some interesting question also that interested for the different kind of hybrid energy store solutions or the backup plans. Fine. Thanks for your responses. So I think poll will still be open. You can still register your responses in the poll in the poll window. And we can start with our presentation. So where we will talk about more towards automotive and some part of it the stationary applications also. So now let's see, when we talk about fuel cells and electrolyzer, and when we are very specific about automotive applications, so then automotive, I can see there are a few use cases. Majority wise, people want to work on the PEM fuel cells and they want to have the PEM fuel cell two-wheeler, three-wheeler, and in some cases, I can see some developments are there where they want to make up planes or the, let's say, airplanes for the net zero energy. So, but to start developing those fuel cells and electrolyzer, what I can say, you have to start from the fundamentals. And fundamentally, if you see fuel cell is a device, a very simple device, where if you see unit cell level, in unit cell level, you have these fuel cell, where we have three functional layer, a functional layer called anode, cathode, and separator. And there is a channels which provides a flow. So basically, there are three layers which is doing all this magic, where fuel is coming into the channels, going to the electrode. At electrode, it is reacting, giving electrons in case of fuel cells based on the anode or cathode, and then the unreacted fuel is passing through. So that way, entire magic happens at this three functional layer. So if you want to understand fundamentally how this fuel cell is working, and if you know the reaction technology, you want to work on the development or enhancement of the performance of that particular part, you want to enhance the life of that particular fuel cell, then you should know what's happening in these three layers. So to know what's happening in these three layers, we should know what is happening in the unit cells. So here, what we can do, we can incorporate all these three layers, where we have geometrically incorporate all three layers, and then we can deploy the electrochemistry, transport phenomena, and multi-phase flow. Multi-phase flow comes in picture when we have the low temperature fuel cells and electrolyzer. So when we deploy all these three physics all together into this functional layer, then we can understand how our fuel cell is behaving. So here, the modeling scale wise, you may have one scale which is very fundamental, which is unit cell scale. And once you understand how this particular cell is behaving, then you may want to get and pack this particular cell around the bipolar plate. This bipolar plate, where it is about the flow arrangement, how we will provide the flow to the all three functional layers. So now the next modeling scale will be bipolar plate scale. So here we have already these three layers available. Now additional these bipolar plates are deployed there. So these bipolar plates will give you the flow arrangement, and then now you can see, because of flow arrangement, the flow fuel provided to the cell may be varying. So in this fuel provided to the cell, if you see, if they are not sufficient enough to the, or they are not uniform, then what we will see the ununiform utilization of the fuel, and that may create some local problems. So when I say local problem, that may be the overutilization or underutilization of the fuel. That may lead to the some kind of degradation. So if fuel contains some kind of sulfur, carbon, some kind of hydrocarbons, and then the fuel cell is not tolerant about it. So then if you overutilization may give you different type of stress conditions as well. So once you know how fuel cell is working, then bipolar plate also is an important part where you want to work on, and now you want to sandwich your three functional layer into the bipolar plate, and there also you will require electrochemistry, transport phenomena, and multi-phase flow. So so now if you want to go one scale above, then we have this bipolar plate scale level model, where one complete cell, including their bipolar plate, is now ready, and we know how one cell will perform. So from till this point, our fundamental understanding is developed how fuel cell will behave and it will work. Now, the single cell may not be sufficient to power your requirements like automotive or stationary applications. So we need huge stacks to be built, and those stacks should be arranged in a different manner to provide your desired power. So here, what we can see, when we change the scale, the problem faced by us will change. So here, if you see the unit scale, the problem is fundamental electrochemistry, microstructure, electrode performance, and then how my electrode will get consumed. So kinetics and or potentials are the main focus. wherein in bipolar plate, how flow will get distributed to the cell. So the flow is the problem become flow dominant, and then we see multi-phase flow and transport phenomena will be dominant in this case. But when we stack the cell, now connection between cells and how we will supplying the fuel to the complete stack, and then it should be uniform to the entire layer of the cells. So all those also will become important. Now at the stack level, we want to arrange the cells like the different. We want to describe the channel geometry, bipolar cells, and then describing the electrode assembly as in layers. So we will still keep all these three fundamental level modeling here, but we are keep on adding details. So the problem will be we will be now scale up. So in scale up, the additional phenomena like flow and the connection between two layers will become dominant. So all these three modeling scale level we can work on. So where we can work on the fundamental level, we can work on one single cell level, the single cell level where including bipolar plate, and we can combine all those cells and stack them. So these examples you will see later in the coming slides, where how one GUI can help you to design all these three levels. So let's just take an example to understand this. We can take an example of alkaline electrolyzer stack. So here we can see there's an industrial level stack where these are the top plate, top and bottom plate. Between them, we have these layers are stacked. So each layer each stack contains all three layers, anode cathode separator and their connections. So that way I can see there are 20 cells in this particular stack. If I want to show you in detail, so you can see this is a stack where we have 20 repeating units, and each unit I can say, if I will see the zoom view, which is the 10 times zoom view, I have one bipolar plate, I have oxygen outlet, hydrogen outlet, inlets for both surfaces, and anode surface, cathode surface, and electrolyte inlet. So what I can see, there is a detailed fundamental structure. When we stack them, then you will get this complete stack ready for you. So when we stack it, so what we are trying to observe here, we in this cell, in this particular model, we will see in the results like how ion contacts are there. If there is any shunt current because of parasitic shunt current, then how that may affect my performance. And we can see the inlet and outlet. At the inlet and outlet, if we have a shunt current, how they will affect the performance. So here the study will be focused on the electrons and ion conduction within the electrode and electrolyte phase. Even we have this complete stack available. So now just see the scale where we have all functional layers like anode cathode separator, and then they are available in the units of 20, and then in the repeating units. So they are arranged there. And when we see the potential, so now just see when we operate this cell for your desired condition. So let's say we are operating at 1.8 volt. So at 1.8 volt, if you see the electrode phase potential, so when we make series of 20 cells into 1.8 volt, so expected voltage will be 35 volt. So the one side it is 0, and then we have 35 volt. So this verifies that your cell is having well distributed electrode potential. So this we can measure in experiment also. But interestingly, things which we cannot measure in experiment will be your electrolyte potential. So electrolyte, if you see, they also, this is now it is at 1.8 volt. Electrolyte potential graph, we can get it from this particular place. So your fuel is going, say in this electrolyzer, so your water is going in. We are producing hydrogen by deploying this voltage. So we can operate this particular cell or stack into a galvanostatic mode where we can fix current. We can operate this cell into, or the stack into the potential static mode where we can fix potential, or else we know there is a fixed power which I want to draw or I want to provide. So then I want to do the energy balance for that. So then I can operate in that mode also. So here we can identify the potential areas for improvement to optimize the design and operations by seeing that what is the how electrolysis reactions are occurring in the most intensively. So that is the main functioning where we see how electrolyzer will function. But there is one side reaction which we can say degradation, which may which may leads to the loss in capacity or loss in efficiency. So here we can see there will be some parasitic current which is flowing through the manifold or the channels. So then we can analyze the impact of design of parameter like gas separations, and the shunt current in the electrolyzer stack. So here again the potential is maintained, and we can see how electrolyte, or the when we say ions are available in the liquid, what is their potential and how they will move. So we can consider the shunt current observed between cells into the inlet and outlet. So we observed the performance-wise how things are performing, and then if we have any problem like shunt current in this case, so that shunt current also can be plotted in this manner. Now, 3D wise, we know okay how things are functioning, but I'm interested to know in the overall performance wise. So here, if I have the shunt current, then hydrogen crossover and hydrogen upper and in lower, and hydrogen this is the current in the upper layers and the lower layers. So here we can see. So what is if we see the cell number two have the shunt current which is lower, and then as we go along, then shunt current is changing. Similar way for the oxygen side also. So shunt current is changing its trend when we go from upper layer to lower layer. So this tells us that okay, when we lower the channel, shunt current is generally higher in the lower channels, and the lower electrolyte conductivity in the upper channels reduces the shunt current. So once we know this behavior is there, so if we can do something about it by providing the different inlets at different layers, so we can reduce the shunt current and we can gain back our efficiency. So this is the spatio-temporal behavior where spatially we know how shunt current is there, and then how it is impacting layer-wise. So that also gives an idea, and ultimately we want to know Coulombic efficiency. So whatever current we are giving, are we getting the similar amount of hydrogen from there? So when we have a stack current varying from let's say 500 to the let's say 3,500, then the efficiency is going up. So when we operate at lower let's say current, then the Coulombic efficiency is less. But when we operate around let's say 3,000 or 3,500 ampere, then efficiency is approaching almost 95%. So these kind of polarization curves also can be obtained, and then now we can see one energy efficiency. So this is a two different type of efficiency which we can see. One will be our Coulombic, where whatever ions we are giving, are they converting into hydrogen, or energy efficiency, where whatever energy we are giving or the current we are giving, then are we being energy efficient? So here what we can observe that both are not similar, they are a bit different. So we can get the more Coulombic efficiency when we go for higher current, but at the same time we are getting lesser energy efficiency when we go beyond 1,000 or 1,500 amperes. So this optimization, if you want to do, so then if I want to be energy efficient, I will operate at 1,500 ampere. And if I want to be Coulombic efficient, then I will operate for higher current. So here the efficiency is lower for lower stack current. Why? So for lower stack current, the shunt currents are larger. And for energy efficiency, we can see the efficiency is lower for low current due to the parasitic current losses. So then higher stack current and polarization efficient will be dominant. So in the both cases, we say that if we operate at lower temperature, lower current, then we are not Coulombic efficient, we are not energy efficient. So we should operate around somewhere wherever we have more energy efficiency and Coulombic efficiency. So these kind of design design decisions, like where we should have the inlet, like at what channel we should have inlet, and then at what operating condition we have to operate. We can make some sense out of it, where we are not going for any approximation. We are solving our all three levels, where we have a single cell level, we have a bipolar plate level, and we are going towards a complete stack level models. So this way, one detailed model give you different insights. So if you, let's say we have a different type of fuse, let's say if we change the setup, so let's say we are at SOFCs, which is operating at let's say 800 degrees Celsius, and then now the membrane here will be ceramic. So then it is generally made of YZ and SCD, and we want to draw 1 ampere. So now how we can approach this particular problem? So let's say we have all these three functional layers as we discussed. So we have a ceramic membrane, cathode, anode, and then we have an open side where air side it is open, but fuel side we have H2O per inlet, which is going in, and then flow will get distributed in these channels, and then there is the outlet. So we are taking care of all these functional layers. They're all fundamental levels. So we will see the mass transfer into the hydrogen and water, as well as the momentum transport. Okay, so once we solve this, can we see how things looks inside the cell? Also, here we say the overall how stack is performing, but can we go in deep dive inside the layers? So this particular example shows the same thing, where when we have the setup, so now I can see how hydrogen is going in. Hydrogen going in, it is taking electron, giving you hydrogen, giving you oxide ions. So along the length, what is my flow rate which I have? So I can see flow rate is higher at inlet, and then at outlet again the flow rate increases, and the flow distribution also is visible to us. So at the walls of those channels, I can see the flow is lower as we are solving for flow in the with the no flow to the wall conditions. And correspond to that, we can see the molar fraction of hydrogen and current density. So hydrogen fraction was lower at the inlet, and as we go along, we are increasing our hydrogen fraction as hydrogen is being produced. So what we'll see, we'll operate the cell at 20% excess H2O with relation to current density stoichiometry is 1.2. So hydrogen molar fraction almost 100% in the same region close to the outlet. So here we can see almost 100% hydrogen is available. So which is which correspond to this flow inlet. So we have the uniform flow, and then along the flow, if you see this reaction is followed, and because of this reaction, we see hydrogen H2O is being supplied to here, and then we are generating hydrogen. So how hydrogen being generated, that is can be confirmed by this current, and this current is being produced locally. So we can monitor the local current densities also. So initially we have higher current density because we have higher fuel that can get converted, but along the flow, fuel will get reduced, or fuel, which means like say we are talking about hydro H2O, which is reducing. So now at later part of it, we don't need to deploy much current, and still we are getting higher let's say hydrogen mole fractions. So both here, what we can confirm there is a flow which is uniform, but the conversion is not uniform. So as we can see here, when we started being produced from this place, and ultimately till this outlet, we are producing hydrogen, but spatially there is a variation. So what I can observe, that at one location we are having higher utilization, at some location we are having lower utilization, and if this is related to stress somehow, so which is ultimately you will observe that there is a stress related to that. So when you have different current at different location, which will lead to different stresses at different locations, and you may lead to instability on your cell. So instability in your cell mechanically may lead to cracking or any kind of crack formation in your membrane. So these insights, which you can see locally, if you can see the flow systems also, in flow wise, we have this density which is higher at initially, and then it goes down because we are producing hydrogen. And similar way, dynamic viscosity also changed. So with these different plots, which is coming from our fundamental understanding, I can give you insights to work on your fuel cell, or else to calculate the efficiency for your fuel cells or electrolyzer, and then you may end up getting one better fuel cells. So let's just take one example of on the time side also. Until now we talked about the electrolyzers. Now let's just see one fuel cell. In fuel cell, this we saw in the beginning. So now this fuel cell, again we can have this detailed geometry where two cells are stacked to each other. So where we have two channels, and three different layers are available. So we have MEA. So here we want to solve for electrochemical reactions, charge transport, heat transfer, and electroosmotic water trap, as we are talking about the low temperature fuel cell. So at low temperature fuel cells, we have to deal with the water transport and water management as well. So now again, the similar plots, when we deploy all those physics all together, we can see on the GUI how those physics will look like. So let's say I'm operating at 0.5 volt at anode side and cathode side, both sides we can see. So there is electric potential. So electric potential at this side is varying in this range, and then we have electric potential at positive side. So cathode side we have anti-potential, negative side we are mostly grounding it, so the potential is near to ground. So we fuel side or fuel side, we are just making it ground, and cathode side we are making 0.5 volt. So then here we are maintaining the scenario or the favorable condition to convert hydrogen into the hydrogen into the fuel, into the H2O, and getting the current out of it. So because of this, we can see this variation. The potential drop which we are observing is 200 millivolt. So this 200 millivolt at 0.5 volt we are observing. That is due to the stem and then for loss calculation in GDL. Now, if we want to maintain the thermal balance or the thermal management also, so locally what we can observe at 0.5 volt, whole cell having at the MEA or wherever the actions are happening or magic is happening, where current is being produced, the sources are higher. So then we can see higher temperature at the MEA, which is 80 degrees Celsius. And as we go away from this MEA, we can see temperature is coming down. So we want to, but we don't want to raise the temperature more than 80 degrees Celsius. So we have to remove this heat. So then we have deployed these cooling channels. So in cooling channels, what we can say at this location, we have inlet, which is coming at 70 degrees Celsius, and outlet, we can see 2 degrees of rise, which is along the flow. So to maintain the temperature at 80 degrees Celsius, we have to say fix what will be the inlet temperature and what will be the inlet flow rate. So here we can see more than 10 degree difference in the compartment of inlet temperature we can see. So the highest temperature are found in MEA, and then temperature increases more than 10 degrees Celsius in this entire range, which we can observe. So it correspond to the other features also. So now we can see RH, which is relative humidity, is changing along the flow with correspond to that. So when we say RH is going high, and current distribution is also changing in this particular direction. So when we get these kind of insights from simulations, then we know how we have to operate it, and then how we will move towards our improvement of the cells. So let's just see these examples or discuss these examples towards towards the automotive, because people deploying PEM fuel cells majority wise in the vehicles. So in vehicle, what we can see, fuel cells can give you constant power, but the area of improvement will be as we discuss with the different, let's say, examples. So here the cooling channels, the how membranes are associated, what will be the thicknesses of your electrodes, and then will they be mechanically stable, and what kind of losses which we will obtain. All those things can be figured out by this place. So till now we talked about the single cell. Now, if you want to get a desired power, so that desired power can be obtained only by stacking the cells. So let's see when we have a cell which we want to stack, then how that can be stacked. So to stack the cells, we know that there will be channels. So there will be MEA available. And in this MEA, we have those inlet channels for hydrogen, hydrogen outlet, end plates, and then these are the different patterns where fuel can come out. Now to deploy this, we can use the same GUI, similar graphical user interface, where in the COMSOL, now I can introduce you a bit about the COMSOL and implementation. So here, if you see any modeling, in the modeling, what we can see, the first of all, which we want to deploy the geometry. So here in this COMSOL graphical user interface, you can see three sections. One will be a model builder, where you can control everything. So what entries or details to be changed, that will be available in the settings window. So let's say if I will click on the geometry, so all geometry related settings will be visible here. And then geometrically, we can see all those details in third column. So first of all, I want to get the geometry. I want to work on a space dependent model where I have this geometry available. I will get the geometry. Then I can identify each and every material which is made of different materials, like membrane is made of Nephyon, or your electrode is made of your carbon paper. In case of high temperature fuel cell, it will be your nickel, YZ, and other materials. And in case of channels, you may have the steel plates or any different type of layers. So here, what we can see, we have we can assign the materials, and then we can deploy the physics out of here. So here in the physics wise, we know the fuel cell will be governed by the hardened fuel cell interface. There will be some flow in porous media. So we have Darcy law, and I want to see the thermal management part of it. So here we have a heat transfer in porous media. So with this, with deploying these physics, all these physics should talk to each other. So then this multiphysics node will be there, which can interact, which can help you to make interaction between all these three physics deployed. You may think of, let's say, I have one more physics also available, which is, let's say, structural mechanics, and I want to see structurally when cell is operating, how structurally cell will perform. So let's say you have one high temperature flow is coming in, and then now you want to know structurally will cell will withstand that particular pressure, and at the same time I want to draw the current also. So here on the same GUI, you can just go to the physics, and then you can add that particular physics as well. So this is a workflow where we can define our functions, parameters, we can define geometry, we can define material, connections between them, and then we can mesh that particular geometry, solve those let's say single studies or sequence of studies, and ultimately we can generate the results out of it. So here we will open this model to you after this presentation, and then see how the model looks like. So when we have this kind of setup, so what we can do out of it. So when we have this kind of setup available, so what we want to try and see optimize that particular setup. So here, once we know how cell is performing, what is the functioning, what is the area utilized, how much flow is required, what temperature to be maintained, what inlet temperature to be maintained for coolant. In some cases, when you are at let's say colder environment, you want to heat up the cell, so then there will be hot fluid which is coming in the cooling channels. It's very contradictory to say that we have the like hot fluid in the coolant channels, but it depends like what conditions we want to work with. So in this here we can in this modules we can develop and optimize the designs. We can incorporate the diverse physics, and we can work on different parameters which is available to us. So you may ask this question that like, do we have any case study where any automotive persons utilize COMSOL or work on COMSOL to get any specific design which may not be intuitive or which may not be obvious? So I can share one case study with you. So in this case study, what we can see, we have this hardened fuel cell development by Toyota. So generally, you can see the channels in the bipolar plate. They may be straight, serpentine, or different type of channels. But COMSOL can help you, or this COMSOL platform can help you to design something which is very non-intuitive, or which is something very new and some new innovation. So here, the Toyota Research Center, they wanted to design the bipolar plate for their fuel cell powered truck, cars, or even the entire city. So the simulation work has been conducted where they started with this random or different type of channels. So as we observe that the channels may play an important role to supply the fluid or fuel into the plate. So when we supply the proper fuel to the all sections, so then we may have the uniform utilizations. So here we can take inspiration from our bioresembles or natural fluid reactant distribution system like leaves, lungs, and blood vessels. So what they say, they will have one main branch where we have a thicker branch, and then later they convert into a smaller branches to supply the fuel or supply the required things at last miles. So what Toyota team got inspired by this bio-resembled or the bio-inspired designs, and then they formulated a problem where they used the COMSOL multiphysics fuel cell interface, and then they combined this fuel cell interface with the topology optimization. So they optimized the entire topology where they started with different designs. So here we can see, but with different designs is giving you different current distribution to your fuel cells systems. So here, if we go for this kind of designs, then we may have the better distribution of our fuel here. So the goal was to get the let's say uniform distribution of our fuel, which will lead to the uniform current generation. and that may resolve the multiple problems which may occur into the our fuel cell systems. So here, what we can see, we have a new design which is prototyped and deployed to the fuel cells and got the increased power output from that particular cells. So the idea was that we know the fundamentals that okay, fuel distribution may change your fuel cell performance, and when how to change the distribution, they did some design, and then ultimately they got inspired by these natural fluid reactant systems, distribution systems, and try to optimize the design. So they left this particular complete optimization on COMSOL by combining fuel cells and then the topology optimizations. So let's just see how these particular things may look in the COMSOL interface itself. So let's see, when you open COMSOL, this is the interface which you will see the first time when you open COMSOL. And then when you want to work on any kind of system, so then you have to follow this model wizard, where we can follow this model wizard. And then here I want to choose what space dimension I will work on. So let's say I want to work on a 3D model. And then now I will choose what physics interface will be useful for us. So in this case, the phase interface which I want will be available in the electrochemistry. In electrochemistry, I can choose this, let's say, hydrogen fuel cell, and then I have the template available for proton exchange membrane. So this proton exchange membrane will be for your single cell, will be for your, let's say, entire stack. So this is the only interface which will be required for either modeling fuels, single cell, or either modeling the complete stack. So let's say I will add this. Now I want to work on the thermal management part also. So then I will go to heat transfer part, and then I know that there will be solids and fluids, both are available. So then I will add the heat transfer in solid and fluids. I will add this. In some cases, let's say you may want to see any kind of structural changes as well along the flow, or along the functioning. So then I can add this structural mechanics or add solid mechanics as well. So let's say add this, and then I can go for the study. So here I know that available study which will be possible for my given physics setup. So I can use this physics setup and choose the type of study. So here I can see some optimization study, which is shape optimization, topology optimization. In heat transfer, it is thermal perturbation for frequency domain. For hydrogen fuel cell, it will be impedance study, time dependent study, and we can see some fundamental study like stationary and time dependent will be available. So let's say I want to do the topology optimization, which is in stationary. So I can choose this, and once I will click the done button, I will reach to an interface where I can provide all those details. So this is the first view or GUI where I can define this particular problem. And as I mentioned, you will reach to an interface where it will ask for geometry. So you can see it is asking for a geometry. So here we can import geometry, which is built in any third-party CAD tool, or we can create geometry here itself. So once you import geometry, then again assign material here. So again, material can be imported from the COMSOL library, where uh, uh, we can see what kind of materials are available to model, and then we can deploy physics. Now I want to maintain the coupling between them. So to do the coupling, I will go to multiphysics. I will right click, and I can see the couplings which is available to me. So I can see electrochemical heating. Electrochemical heating is combining the fuel cells and heat transfer in solids. And how they are combining both of them, we can visualize the equations behind that. I can see one more coupling is possible, which is thermal expansion, because I am having the structural mechanics and the heat transfer. So this thermal expansion also can be combined, and I can solve that thermal expansion and then fluid cooling also. So this way, I can create one coupled model based on our given physics, and I can solve and generate some results. So let's see one of the example which is already solved here for the fuel cell stack. So then you can see some template examples which can help you to start with modeling. So let's say we have example which is towards the fuel cell or stack. So let's say we have stack cooling example. Let's open this. Okay, so here now this is the complete stack level model where we have our fuel cell, and let's say I want to identify where is my electrolyte phase or the membrane phase. So if I can see that these are the membranes which is being deployed, and if I will zoom in, I can literally see which are the membrane domain. So there will be a membrane domain. You can see highlighted in blue. I can see my diffusion layer for hydrogen, diffusion layer for oxygen, and then electrode or the manifolds for them also. So you can see the hydrogen manifold, oxygen manifold. So all those details are listed, and then I can see my diffusion electrode as well. So this way I can see each and every detail for this particular fuel cell, and material wise I'm using the steel, water, and then Nephon, which is EW1100. So once we have this kind of multiphysics model, then I can visualize the results out of it, where I can see these sort of results here. So you can see how fuel cell is arranged, which I explained to you, and ultimately I can see the temperature part. So what is the temperature distribution in my entire MEA? I can see the temperature distribution along the z coordinates of in the manifolds of the channels. So based on different channels, what is the current temperature distribution, and we can see the water activity in the entire fuel cell. So this way, I can define the different problems here, and I can work on an entire fuel cell stack in this case. And this model is already built, but if you want some improvement or you want to add some details on top of it, so then we can go to the physics, and you can additionally add some more equations here. Like you can add solid mechanics, we can add any kind of optimization. So optimization wise here, let's say we have mathematics, and I can see optimization studies are already available. We can do some kind of sensitivity analysis, and we can see some general optimization as well. So with this, I think I have done with my presentation and a quick demo to you. So I can launch one poll question, and then while responding to this poll question, we can take up the questions. So now I think we can have some questions about it. Some questions we already have into the webinar chat, but let's see what questions we have into our questions tab. So we can take up some questions now. So I request team to read out some questions which we got in this session.
Sure. So one of the questions is, I am working with high temperature solid oxide proton exchange based electrolysis. Is this supported?
Okay, so yes, so if you are working on a high temperature proton based membrane electrolysis, so this will be supported, and I can say that will be much more simpler than the low temperature, because at low temperature you will deal with one more additional problem, which we call water flooding of the membrane. But at a high temperature, we don't have that kind of issues. So we can get rid of one issue. That is a very good solutions for PEM fuel cells, where we can go for high temperature. But at higher temperature, you see the conductivity of protons will become challenging. So the Nephon may not support the proton conduction at high temperature, as it is not liquid, it is not have some kind of water content, because at high temperature there will not be water content in Nephon. So only problem which you will see the finding out a new material. But modeling study wise, you can still see those kind of examples. So one of the example, if you want to see, that is available in this model library also. So where we have the high temperature PEM fuel cell. So high temperature PEM is supported, and you can find out some of the examples available. And if you want to know more details, you can let us know, and you can be in touch with us. You can write to us. I hope I answers the query, and if you have any follow-up query, please let us know.
Thank you, Dr. Rustam. Our next question is how taking H2O as gas phase for electrolyzer make physical replication of actual result. Is there any demo available for water in liquid phase for PEM electrolyzer simulation in COMSOL?
Okay, so there are two things. One is that you are providing liquid water, so then you can see these are liquid water, how we can deal with liquid water. There's one example available, you can see here. And one example I showed you on the presentation where we are directly giving the, let's say, water as in steam form. So in water in steam form, generally given to the electrolyzer where they are working at high temperature, more than 100 degrees Celsius. So it is just no inlet condition which you can provide and you can work with. So that is feasible. Going high temperature, generally I can see it's a bit simpler than the lower temperature. Only thing is that now we will be facing the challenge from the material property side. So material properties may not be accurate, may not be good enough, or you may not find material which may operate or give you desired properties like conductivity of your ions or the catalytic activity at that high temperature. So possibility wise, you can provide your liquid water. So the example is here. And for other examples which you see, they are working on the, let's say, vapor form. So both examples you can see, and then in electrolyzer, you will find the both kind of examples where we have, let's say, low temperature and high temperature fuel cells where where steam is going at steam or the liquid form both.
Okay. Our next question is, can I include capillary pressure effects in the gas diffusion layers?
Yes. So I think this is one interesting question. So where if you see the hydrogen fuel cell, and when I'm solving the Darcy law in detail here itself. So let's say I'm solving the Darcy law for the momentum. So when I will go to the let's say diffusion layer, here I can incorporate the let's say pole-wall interaction. So that will be accounting for those capillary reactions. So capillary reaction is already incorporated there. So your mass transport will be there because of convection, diffusion, and capillary reaction. Additionally, you can account for those like pore wall interactions. So that will account for those kind of Knudsen correction also. So these kind of features where we can define the pore diameter, and then capillary reaction also can be incorporated there.
Thank you for answering that, Dr. Rustam. Our next question is, in selecting model, what is the difference between selecting heater transfer in solid and heat transfer in fluid instead of conjugate heat transfer?
Okay, so when you see when we go for the model wizard, and then I want to solve for 3D, and let's say I have heat transfer. In heat transfer, I have heat transfer in solid and fluids and conjugate heat transfer. So in heat transfer in solid and fluids, what if I will add this? I am having only this heat transfer in solid and fluid interface where I am only tracking temperature, and I'm saying I know the flow field. So I can input the flow field and I can give the velocity field. And I can work with that where I'm ignoring, or I'm simplifying the model. But let's say I can let's just remove this and I can add this conjugate heat transfer with laminar flow. So when I will add this, then along with the heat transfer in solid and fluids, I'm additionally solving laminar flow. So here I don't know flow. I want to solve for flow also, where both physics would talk to each other, they will interact to each other. Then I will have this non-isothermal flow systems available. So when this conjugate heat transfer, where we are solving one more additional equation, which is laminar flow, wherein heat transfer in solid and fluids, we say that we know the flow field and we are just deploying it. So advanced form of heat transfer will be your conjugate heat transfer, where we are solving those additional 5 variables. Sometimes they may not be required because the flow is only one dimensional and we know the velocity out of it. So we can ignore, or we can simplify, or we can make model quicker without solving this laminar flow. So both are similar, but the conjugate heat transfer is extension of heat transfer in solid and fluids, where we are solving one more additional equation with that.
All right. Our last question before we end today's session: how many cells can be modeled in battery pack modeling?
It is slightly different from this session, but we can still add, let's say there is no limitation that how many cells you can have into the battery pack or even in the the electrolyzer. So there is no limitation. Only limitation will be from the hardware side, that how can hardware handle those many number of degrees of freedom. So it's only depends on how many degrees of freedom your system can handle. If you have a network license and you have infinite resources mesh wise, then there is no limitation. You can have a very huge stack. You can, let's say, if you see the stack given by the Bloom Energy, so that complete stack itself can be simulated. Complete container can be simulated within the software itself if you have sufficient computation resources are available to you. Yep.
Thank you, Dr. Rustam, for sharing your insights today. And we thank COMSOL for letting us host this session today. It was a very insightful discussion. And for our viewers, we will keep coming back with more such insightful discussions. Thank you all for taking the time out today to hear out COMSOL and Dr. Rustam. Thank you, everyone.
Yep. Thank you. Thanks for attending and participating.